Hello and welcome to the first of the lectures in this week 9 of the course titled Approximate Reasoning Using Fuzzy Set Theory, a course offered over the NPTEL platform. In the last week, we discussed the interpolativity of fuzzy inference mechanisms, specifically that of FRIs predominantly, wherein we looked at the compositional rule of inference and the Bandler cohort subproduct. Note that when we discussed this, we were assuming the operations to come from a residuated lattice. Given a set of rules, single input, single output rules, the Q matrix was formed from the antecedents and the matrix P was formed from the consequence. This led us to study the solvability of fuzzy relational equations, and through that we came up with conditions on interpolativity of the underlying FRI mechanisms. For instance, when the T and IT form a residual pair, in the case of CRI, we are looking at Q sub T composed with R is equal to P. We saw that this equation has a solution for R when Q and P are fixed. Q is given in terms of the antecedents and P is formed from the consequence. We saw that this system has a solution if and only if this R cap, which is the Q transpose inf IT composed with P, is a solution, it's a maximal solution. Similarly, in the case of Bandler cohort subproduct, we have seen that Q inf IT composed with R is equal to P. When Q and P are fixed, it has a solution for R if and only if R check, which is the Q transpose with sub T composed with P, if this is a solution and if it is a minimal solution. Now the question that comes to mind is, from the fuzzy relational equations, we have obtained the interpolativity of the underlying FRIs. But when we have multiple rules, we have two inference strategies, that of FATI and FITA. Now it is clear that in the case under which interpolativity is ensured, we are looking at a single relation, which means it is in fact the FATI inference strategy. First aggregate, then infer. Then the natural question that comes up is, what happens to FITA in this case? Are these two same? Let's take a couple of examples and check it. This was the first example that we have seen. Note that here the composition is sub T, so we are looking at CRI, and we are using the Gödel implication, which is the residual of the minimum T0. Now we have seen that R cap is given as this, and when we asked the question, is it interpolative, all we did was we took A1 and composed it with R cap, and we found that yes, we were getting B1. Similarly, when we took A2 and composed it with R cap, we were getting B2. Note that this is a single relation which we are using, which is composed of the two relations obtained from these two rules using the Gödel implication, and we are taking a minimum over. So this is clearly falling into the FATI region. What happens if we use FITA? Note also the other examples that we have considered, where we changed it to sub TLK, so it's still CRI but with the Ukashevich T0, and the corresponding Ukashevich implication, which is its residual, has been used, and we saw that once again we obtain interpolativity. We have seen also an example for the BKS inference mechanism, where we took inf ILK, that means the implication was Ukashevich implication. So clearly the corresponding D residuum is the Ukashevich T0, and that's what we have considered. You can also see that this is the case here, where we are obtaining the relation using the T norm there, A1 transpose B1 using the T norm here, and then we are taking a max over. Once again, we have seen that we obtain interpolativity. Let's consider a couple of examples from this and see what happens when we actually apply the FITA inference strategy. That is, first infer, then aggregate. The question is, are they equal? Because interpolativity seems to be available only when we have this FATI inference strategy. Now, this is the first example we have seen. Sub-min composition with the Gödel implication giving the relation between the rules. These are the AIs and BIs, and these are the individual relations. Let's ask whether it is interpolated. That means applying theta and seeing whether we get the same value that we got in the case of FATI. In the case of FATI, we knew that it is interpolated. That is, if you give A1, you will get B1, and A2, you will get B2. So now, in the case of theta, we are taking A1 and composing with R1. Let's write this. So we are looking at 1, 0, 0.3 composed with R1. R1 is given as 0.4, 0.8, 1, 1, 1, 1. Note that we are using sup-min composition. So when we apply this, this is max of 1 and 0.4 is 0.4, 0 and 0 and 1 is 0, 0.3 and 1 is 0. Similarly, the second component will be max of 1 and 0.8 is 0.8, 0 and 1 is 0, and 0.3 and 1 is in fact 0.3. So now from these two, what we get is 0.4, 0.8, which clearly is your B1. So we see here A1 with composed with R1 is B1. However, note we are looking at theta inference. That means A1 has to be composed with R1 to get B1 1 dash. Then A1 has to be composed with R2 also. So let's take the R2 relation, which is 1, 1, 0.3, 0.7, 0.3, 1. So now we are going to compose 1, 0, 0.3, sup-min. Allow me to write it directly. 1, 1 is 1 max. So then essentially it is 1. Once again, 1 and 1, it is 1. Max of this cannot be greater than 1. So it is 1, 1. So what we get is 1, 1. Now, these are individual inferences, PA dashes. So we need to aggregate them using G, which is min. And what we find is, in fact, we get B1 itself. Let's look at A2, whether we infer using the theta strategy, whether it gives B2. So once again, allow me to write it here. So A2 is 0, 1, 0.7. Remember, A1 and A2, they are normal and they form a Rushmini partition. So when you apply sup-min composition, 0, 1, 0.7, it is 1, 0, 0.8 is 0, 1 and 1 is 1, so that's a maximum. You don't get any better than that. That's what you get. So this is what we get as B21 dash. One more. So what is B22 dash? That is A2 composed with R2. So once again, let's write this. A2 is 0, 1, 0.7. Now, when you compose it, 0 and 1 is 0, 1 and 0.3 is 0.3, 7 and 0.3 is 0.3, so you get 0.3, 0 and 1 is 0, 1 and 0.7 is 0.7, 0.7, so the max is 0.7. So this is our B22 dash. So it is 0.3, 0.7. Now, once again, applying the aggregation, which is min operation here, G of this is in fact 0.3, 0.7, which is B2. So in this case, we see that when we give the antecedents as the inputs, both FATI and theta seem to be interpolated. Now what about the case of PKs? It can be easily verified. These are the relations that we get, and if you give A1 to R1, we get this 0.4, 0.8. If you give A1 to R2, we actually get 0, 0. And now note that the maximum is the aggregation operator. So when you aggregate these two, we get 0.4, 0.8, which is B1. Similarly, if you take A2 and do the theta inference, A2 as the input and do the theta inference, we obtain the overall output to actually be B2. So from these two examples, it appears that FATI is equal to theta in the case it is actually interpolated. It appears from the numbers that we have taken. But is it really true? Let's once again take the very first example that we considered. So now these are the individual relations and this is the composed relation, the aggregated relation. So let's retain them. A1, B1, A2, B2. This is R1, R2 and the combined relation. which is in this case r cap, because we want it to be interpolative. That's the context in which we are considering this. Let's give a dash to be 1.3.8. So it is something different from either a1 or a2. Let's calculate what happens in the case of this equation. So now a dash is 1.3.8. So what we get is 0.4, 0.3, 0.8, 0.8, 0.3, 0.8. So we get 0.8, 0.8 as the output. Now we need to apply this a dash also to R2. R2 is here. 1.3, 0.8. So max is 1. Again max is 1. So this is 1, 1. Now we aggregate these two local outputs, and what we see is we get 0.8, 0.8 as the B star. Right now we are not discussing interpolativity because a dash is not one of the antecedents. So let's apply the theta inference. So for that, what we have is the combined R, which is the R cap here. So we have 1.3.8 sup min R cap is 0.4, 0.8, 0.3, 0.7, 0.3 and 1. So this is the R cap that we have. If you apply the sup min composition with this, 1, 0.4, 0.3, 0.3 is 0.3, 0.8 and 0.3 is 0.3. So what we get is 0.4, which is the maximum. 1 and 0.8 is 0.8, 0.3, 0.7 is 0.3, 0.8, 1 is 0.8, so the maximum is 0.4, 0.8. Clearly, this is not equal to B star. So if you give a new input, an input which is not one of the antecedents, in this system at least, we have seen a dash, the B dash obtained from theta is not equal to FATI. So just because we have interpolativity, it does not mean that FATI is equal to theta in that context, when the operations are considered like that, when the relation is also considered according to the condition satisfying interpolativity. Now the question arises, is there some situation where we can ensure theta is in fact equal to FATI? Well, this is what we will deal with next. Look at this. This is the FRI system, the CRI system, where only the composition is fixed as sup T. If we take G to be the maximum, that is, if you aggregate it using the maximum, aggregate all the relations using maximum, then it can be shown that theta is in fact equal to FATI. Now, how do we show this? What does it mean? Look at this. What is the theta inference? Theta inference says first infer, then aggregate. So that means given an a dash, we compose it with the Ri and then aggregate it. For the aggregation, we are using max. So this is the theta inference. FATI is, it says first aggregate all the relations and then apply the composition for the given a dash. We want to show that these two are actually same. So what does it mean? So let's start with the FATI inference. So B dash of y according to FATI is a dash circle T supremum I is equal to 1 to n Ri evaluated at a particular y. Note that y element of y is arbitrary. Now let's expand this. So this is supremum x over x a dash of x. Let's use the infix notation star I is equal to 1 to n Ri of x comma 1. Now the star is a t-norm. We know that t-norm is increasing in both the variables. So by monotonicity and also otherwise, it can be shown that any t-norm is distributive over max, which means if you have t of A, B or C, this is equal to T, A comma B or T of A comma C. So using this distributive equation, what we can do is, we can rewrite this like this. We can pull out this quantity. So this becomes x element of x, I is equal to 1 to n. Note that this supremum here is of the elements varying over the domain x, and this or here is the disjunction of the rules I is equal to 1 to n. A dash of x star Ri of x. Now these are maximum or supremum taken over two different domains. Easily we can switch them. You can write this as x element of x, A dash of x star Ri of xy. But note, what is this? This essentially is A dash circle Ri. So we can write this as I is equal to 1 to n A dash circle Ri at xy. Now this is nothing but inferring each one of them for a given I and then aggregating. So clearly this is the FITA inference. What did we start with? We started with FATI inference. This is FATI for us. First we aggregated the rules and then took the A dash and composed it. Now what we have seen is it is same as composing first and then aggregating the outputs. So clearly in this case we see that FITA is equal to FATI when G is equal to max and we use the sup-T composition. Note that here we are not expecting any conditions on the T norm. Any T distributes over max. So that is the only property that we have made use of here. What is interesting is, if you consider R check, which is nothing but the Q transpose sup-T composed with P, if you rewrite this, what you see is this is what is your corresponding relation. It is not R cap, the corresponding R check. So now you see here, it is essentially applying the maximum as the aggregation, and for F we are using the corresponding T norm star itself. So now in this situation, when you use R check, it is clear that G is max and hence FITA will be equal to 40. Note that in this proof that we have seen, we did not specify how Ri is going to be. We have not specified how Ri has been obtained. So you could obtain Ri from any operation F, and in this case the F is the corresponding T norm itself. Similarly, we can show that if you are looking at BKS, the composition is fixed as delta IT. If you take G is equal to min, then we can show that FITA is equal to 40. So once again, let's look at what is it that we are dealing with here. The FITA inference is A dash composed with each of the Ris, and then we are taking the minimum of them because G is min here. That's the aggregation. 40 is about first composing all the relations using the aggregation and then applying the IT. Well, once again, if you start with 40 at a particular Y, we know that there is nothing but A dash Ri apply the particular Y. Write this here. This inf over x element of x, A dash of x implies Ri of xy Now, implication, as we know, is increasing in the second variable, and this is conjunction of the rules. So once again, we can pull this outside and write it as A dash of x implies Ri of xy. Now, once again, interchanging the conjunctions, what we get is Ri of xy. Now, you readily recognize this is nothing but A dash composed with Ri at a particular y, and is equal to, and I is equal to 1 to 8. So clearly, this is the theta inference. So in the case of BKS, no matter what the relation Ri is, what operation F we have used to obtain the Ri, if G is min, you would get FITA and FATI to give the same output for any input A dash. Now notice that if you take the R cap relation, it is given like this, which essentially means it is infimum of AIX implies BAY. So note that what we are interested in is the aggregation that we have used. In this case, it is I is equal, it is actually infimum, which is the minimum. As was mentioned, the operation F is in some sense inconsequential. Of course, in the case of R cap, that gets fixed to be the corresponding implication, the IT that we use. So in that sense, note that for interpolativity in BKS case, we want that R check should be a solution, and if it is a solution, it should be the minimal solution. Whereas here we are asking for R cap. In the presence of R cap is one of those relations which will lead to the FITA and FATI inference being equal. Well, we have seen the relation between FITA and FATI. When will they be equal? Let's see whether the FRI and SBR, two of the major fuzzy inference mechanisms, whether they themselves are related or not. Towards this end, let's recall the graphical illustration that we have seen earlier about how to look at these inferences themselves. Let's look at the FATI inference strategy in an FRI. We are given an A dash, which is the input. We need an output B dash. To obtain this, we are given the ground truth in the form of rules. Now, from these rules, we abstract the relations Ri. So we have n such rules, so we have n such relation. In first aggregate, then infer. First, we aggregate these relations into a single relation R, and we compose A dash with R to obtain our B dash. In the case of first infer, then aggregate strategy, we still have these R relations, but what we are going to do is, instead of aggregating these relations, we are going to compose A dash with R1 to obtain B1 dash, A dash with R2 to obtain B2 dash, so on till obtaining Bn dashes. So locally we are going to compose and obtain local outputs B1 dash, B2 dash, so on till Bn dash. Then after inferring them, we are going to aggregate these outputs to obtain the B dash. So this is the first infer then aggregate strategy. These are the two inference strategies that we have in an FRI. If we look at the similarity based reasoning scheme, what we have is we are given an input A dash and we still need an output B dash, but we are retaining the rules as such. So we have n rules of the form A1 implies B1, A2 implies B2, A3 implies B3, so on till An implies Bn. Now what we do here is, first given this A dash, we are going to match it against each of the antecedents A1, A2, A3, so on to obtain a similarity value S1. So A dash matched with A1 gives us a similarity value S1, with A2 it gives S2, with A3 S3, so on till Sn. Now we take this similarity value Si and modify the corresponding Bi. So S1 modifies B1 to give B1 dash, S2 modifies B2 to give B2 dash, similarly we get B3 dash, so on till Bn dash. So now this is finally aggregated to obtain a B dash. So it appears that the FITA strategy and the SBR mechanism, they seem to have some kind of a correspondence or some kind of a similarity. Let's explore this a little further. Not just this, if you look at the conditions for interpolativity that we have seen in the last week of lectures, they also show some kind of similarities. For instance, look at the interpolativity conditions for an FRI. Of course, we have the assumption that T and IT form a residual pair, so the operations are coming from a residuated lattice. We have seen that one condition to ensure interpolativity, either for CRI or BKS, that all the antecedents are normal and they actually satisfy the antecedents and consequence together, they satisfy this inequality, which we call it the semi-partition inequality. Now, under the same context, when the operations are coming from a residuated lattice, we have seen in the case of SBR such an inequality. Now, the right hand sides are on exactly the same, only the left hand side seems to differ. But does it really? For instance, M is only a matching function. Consider the Z as matching function. So either we could write it like this, or in terms of infixed notation, this is how it appears. And this is exactly the same as what you have in the SP equation. So this gives us an idea as to perhaps SBR and FRI are indeed related. Let's look at this. Let's try to look at CRI as an SBR. That is, an FRI, a fuzzy relational inference like this compositional of inference. Can we look at it as a similarity based reasoning scheme? Once again, we'll fix the residual pair. That means the operations are coming from a residuated lattice. We have seen that when we consider a CRI, if G were max, we got FITA is equal to FATI. And if we consider for the relation R, the R check, where the aggregation is max, clearly FITA will be equal to FATI. The inferences from both the inference strategies will be same. Now we want to show the conditions under which CRI can be looked at as an SBR. Now look at this. This is the form of this CRI. If we take for the rule the relation R check, that means F is star and G is max, the sub T composition. Of course, these are operations are coming from residuated lattices. Then we can show this is equivalent to an SBR inference mechanism. In the SBR inference mechanism, what we have is we have a matching function, a modification function, and aggregation function. Note that we are in the context of looking at them as fuzzy inputs and fuzzy outputs. So H and G, the fuzzifier and defuzzifier, don't come into picture. Now, given the CRI, where the relation is given as R check, that means F is star and G is max, it can be shown that is in fact it is equivalent to an SBR, where the matching function is the Z is matching function, the modification is this is given by the T norm star, and the aggregation is given by max. Let's prove this. This is what we want to prove. We want to show that in the presence of R check, consider R check of x1, which is nothing but A of x star bi of y. We want to show that such a CRI is in fact an SBR. Now, what is the output that we obtain from here for a given B dash? It's nothing but A dash sub T R check of xy. Once again, y element of y is arbitrary. This is equal to sub x element of x A dash of x star. So for I is equal to Ri of x y, which is in this case A of x star B of y, once again, we pull out the distinction over the rules. And what we have is a dash x star aix star biy. Now, note that we can interchange these disjunctions. Even though we should put brackets, because of associativity, we do not have to really worry. However, now look at this. Here we have this bracket here. By associativity, we can put the bracket like this also. Now, if you look at it, this is a disjunction, maximum, a supremum running over x. It has nothing to do with bi because its argument is y. So we could also write this as I is equal to 1 super over x a dash of x star ai of x star bi of y. Now look at this particular quantity. This is in fact exactly mz of a dash a. So now this will give us an SI. Now this is SI star bi of y. So this is our j star, and for aggregation we have g is equal to max. So we see that CRI, when we use the relation R check, we see that it is in fact equivalent to an SBR where the matching function is the Lattice function, the modification is given with the same T norm, and the aggregation is the maximum aggregation. Now, can we look at BKS also as an SBR? Yes, of course we can. But before that, let's revisit some of the properties that are available for us from the residuated lattice structure. Let's look at some of these properties. A few of them we have already known to be useful. For instance, these two properties on the second row are what we have seen as the TF conditionality and the IF conditionality, which were instrumental in showing interpolativity of an FRI in the case we had a single CISO rule. Now, the third equality, the property, is also called the law of importation. We will have reasons to look into this function as a functional equation and in much more detail in one of the upcoming lectures. The last of the properties is essentially the distributivity of conjunction and implication. For instance, this comes from the classical logic tautology, which says that if it is A or B implies C, then this is A implies C and B implies C. So this is how we understand it. P1 or P2 implies Q is P1 implies Q and P2 implies Q. Of course, in this case, I is an infinite, possibly infinite index set. Well, we'll make use of the third and fourth properties in showing that BKS can also be seen as an SBR. Once again, we are in the realms of residuated lattices. We have seen that for a BKS, when G is min, that if you aggregate all the relations using the min operation, then theta is equal to FATI. Now we have seen immediately that the R cap relation essentially aggregates these relations using the minimum operation. Note that for F, it is using the implication itself. We will see that if we use R cap in the presence of infimum IT composition, that means in BKS, if you use R cap, essentially it means G is min and F is the corresponding implication. We can show that it is in fact equivalent to an SBR inference mechanism, where the matching function once again is the Lattice matching function. The modification is given by the corresponding R implication that we are considering, and G, the aggregation, is the minimum aggregation. Let's see how to prove this. So we need to show that FRI is also an SBR, and what we are given is R cap of xy, nothing but and is equal to 1 to n value of x implies value of y. And we already know there are two properties that we are going to make use of, and that is P star Q implies R is equal to P implies R, and also that we have this around we'll make use of both these properties now. So let's look at inferencing using BKS with A dash and R cap. So B dash of y is this. If you had to expand it, it would look like this. In for x element of x, A dash of x implies I is equal to 1 to n. Ri now is Ai of x implying Bi of y. Once again, as we did earlier, we can pull out the conjunction over the rules outside, and what we are left with is A dash of x implies A of x implies B of y. So now you can look at this as P implies Q implies R, which means we can use this property here and then write this as P star Q, which is A dash of x star A of x implies Bi of y. Once again, by swapping the infima, both the infima, what we get is I is equal to 1 to n x element of x A dash of x star I of x implies Bi of y. Now, note that if we consider this quantity, the x here affects only this. So you could look at this as the corresponding PIs and this as the Q. And so what we have is something like PI implies Q over and this we know with respect to this property can be modified like this. When you push it inside, then it actually becomes the supremum over x element of x A dash of x star A of x implies Bi of y. Note once again now is essentially mz of A dash comma Ai, which we know is Si. So this is the similarity value. Now Si is modifying Bi using this J, which is the implication, and this is our G, which is the minimum operation. So we see once again, if we use R cap as the relation in a BKS, then it can be seen as an SBR where the matching function is given as the Lattice matching function, and we take implication for the modification and minimum for the aggregation. Of course, note that these were possible because we assumed the operations to come from a residuated lattice structure, which gave us a lot of properties. Such rich properties helped us in obtaining this equivalence. Let's have a quick recap of what we have seen in this lecture. In this lecture, given an FRI, we asked two questions. Will the FITA and FATI inference strategies, will they be equal? Will they give the same output? And the second question that we discussed was, if an FRI can also be seen as a similarity-based reasoning scheme. In the case of CRI, while it was R cap which ensured interpolativity, that is, if R cap is a solution of the appropriate or the corresponding fuzzy relational equation, we saw that it leads to interpolativity. When I wanted to answer the question of equivalence of FITA and FATI, or whether FRI, this CRI can be looked at as an SBR, it was R check that came to our rescue. That is, if you use R check, employ it to capture the rules, then we know the output from FITA or FATI will remain same, and such a CRI can also be looked at as a similarity-based reasoning scheme where the matching function is essentially the Zardé's matching function. In the case of BKS, the roles are reversed. It is R check which ensures interpolativity if it were a solution of the corresponding fuzzy relational equation. However, it is R cap which ensures that FITA is equal to FATI and allows us to look at BKS itself as a similarity-based reasoning scheme. In the next lectures, we will start to deal with continuity of fuzzy inference systems, both that of fuzzy relational inference and also the similarity-based reasoning schemes. Glad you could join us today for this lecture. Hope to see you soon in the next lecture. Thank you again.